Hey guys, fast video I promise. Something that we haven't talked about called polyprotic acids. The name kind of gives it away. It means many protic, or many protons, which means just more than one. Previously we just looked at weak acids that could donate just one hydrogen. And the classic example, of course, would be hydrochloric acid, which comes from something called hydrogen chloride, which is a gas. Now, if this separates and this bond is broken, leaving you with the H plus ion and the chloride ion, that would be a strong acid because it dissociates, let's just call it 100%. But it can only give one hydrogen. And so it's kind of limited in terms of discussion. Something like what we did in lab, this is called oxalic acid. There are two hydrogens on this molecule. And it could donate two of them, but not all at once. Whenever a hydrogen is donated, what it's going to do, it's going to leave a negative charge. And the strength of that acid is dependent on how stable the negative charge of the conjugate is. Now, there's a number of factors that can stabilize that negative charge. And oxalic acid falls into the category of carboxylic acids because all carboxylic acids are resonance stabilized. For example, if you guys remember resonance, whenever that hydrogen is removed or donated, let's say, so we get the removal or donation of that hydrogen, we get an H plus ion in water that makes H3O plus, and then we get this first conjugate here. This negative charge can actually move because you have a lone pair of electrons that's unbound near a double bond. And this is a pattern of resonance called lone pair next to something called pi bond. And what happens is this lone pair, or any of these lone pairs, can say, let's form a bond, and then this can break and form a lone pair of electrons. And so what you end up getting is something that might look like this. The result of that arrow push, let's get the arrows out of here, is going to give us a alternate form where I've just relocated the negative charge to another oxygen. And so the area that the negative charge is able to move to has expanded. And the larger the area of the negative charge, the more stable the negative charge. And so my ability to distribute a negative charge over a broad area is a factor in how willing a substance is to donate a hydrogen. Now this would be the pKa1. If I was to remove this other hydrogen, that would be the pKa2, or the ability of this to remove, which isn't as likely to occur. Because if I did that, now the removal of this hydrogen gives me another negative charge here that, yes, is resonance stabilized. But when it is, you have this area here that's, oh, come on now. This, let's say I have a negative charge that's distributed here and a negative charge that's distributed, oh, that's ugly. Come on now. A negative charge that's distributed here. These are both negatively charged fields, we'll say, and there's a little bit of repulsion there. So that's going to slightly compress the area. And so something like oxalic acid will definitely, in some situations, donate both of its hydrogens, but not until the time is right, because it will destabilize the area that it can be distributed over. And so when there's more OH species in water, it'll be more likely to donate another hydrogen. You can kind of see that with a titration curve. Okay, so one thing to recognize, or one thing that you may have to do, is look at a molecule, and if you have a good Lewis drawing, that'll be easy to do, and say which hydrogen is going to be most likely to come off. And let's look at this example down here. This is called salicylic acid. And there's a number of reasons why this hydrogen is the most acidic, as opposed to down here. Because if I remove both oxygens, I could evaluate the stability of the negative charge. Now they're both on electronegative elements. Now keep in mind, the negative oxygen is the second most electronegative element besides fluorine. And so here you have an identical situation initially, where the oxygen bears the negative charge, but on this oxygen we have that resonance stabilization. So this ability to relocate that negative charge would tell me that this hydrogen that was here before is more acidic than this one. Another factor is something called inductive stabilization. So let's say, here is something called succinic acid. If I was somehow able to replace a hydrogen here with an electronegative element like a fluorine, that would make this hydrogen more acidic than this one because, if I remove this one, I'd have the identical situation over here. And so if I made that a negative and deleted this one, at first glance you would say, well, both oxygens are resonance stabilized, shouldn't matter. Well, if you have a really electronegative element like fluorine, it's going to want to pull some of that electron density towards itself. It's very hungry for electrons. So this electronegative region will be even more expanded by the presence of a very electronegative element like fluorine. And this would also apply to a situation called oxo acids. Weak acids, yes, that don't completely dissociate, but let's take a look at two situations that are similar but have a very prominent difference in that if I was to look at these two elements or these two substances, the donation of both hydrogens would give me an identical situation in terms of the negative charge being on the oxygen. But the first choice would be more acidic because this fluorine is more electronegative than bromine. And so that would inductively stabilize the negative charge. The fluorine would sort of sense a negative charge on oxygen, and what it would do, it would kind of pull some of that electron density towards itself, so you might see something that looks like that. Bromine's actually less electronegative than oxygen, so oxygen is just going to want to keep that all on its own, so we have a broader distribution area here as opposed to here. So if you see something like this on a post-lab question, how to recognize the most acidic hydrogen, it's just which hydrogen is the most likely to be removed in an aqueous environment, and that's controlled by resonance and induction.